So in this video I want to give you the opportunity to calculate this integral, and what I would like you to do is try it with pen and paper, come back later and I'll go through a detailed solution. So I will see you in a few minutes. Okay, welcome back. Let's look at the solution on the next page. So here is our integral, and we cannot do it by inspection. If there was, say, an x here, we could, but there isn't. And the pattern that we need to spot is this square root here of 1 minus x squared. And if you see a pattern like that and you cannot perform the integral by inspection, it is very likely going to be helpful to make a sign substitution. In other words, we're going to say that x, our variable in the square root, is going to be the sine of theta, and that means that the derivative of x with respect to theta is the cosine of theta. From this definition, we have that theta is the arcsine of x, so it's the inverse sine function. So we take the inverse sine of both sides. Arcsine of x is equal to the arcsine of sine of theta, it's theta. And the key thing that we identify here is that the arcsine function is defined for an angle between minus pi over 2 and pi over 2. So theta has this range. Now, we now want to rewrite the integrand in terms of theta. So the square root of 1 minus x squared is the square root of 1 minus sine squared theta. So it's the square root of cos squared theta. That is the modulus function. So it's equal to the modulus of the cosine of theta. But the key thing to recognize is that because theta is in this range, the cosine function is positive. So cosine of any angle between minus pi over 2 and pi over 2 is positive, so we don't need to write the modulus. We can just say it's the cosine of theta because theta lies in this range. So now, the formula we're going to use is this for a change of variables. The integral of f of x with respect to x is equal to the integral of the function of x rewritten in terms of our lovely new variable, theta. And then you multiply, you insert by hand a factor of dx d theta, and you integrate with respect to theta. Now, we know how to write our integrand because we've set up the square root and we've said that it's just the cosine of theta. Dx d theta we've also calculated, so we can rewrite our integral immediately. So we have the integral, and now the original integrand is 1 over the square root, so it's 1 over the cosine of theta. Remember, we don't need a modulus because theta is between plus and minus pi over 2. And then the dx d theta introduces a factor of cos theta, and they are going to cancel. So we have the integral of 1 with respect to theta, and that's just going to be theta plus an integration constant. And we know what theta is. Theta is the arcsine of x. So this is our result for this integral. So if we make a sign substitution, we can perform this integral, and that is the result we get. And on the next slide, what I want to do is to show if you differentiate this, you get back to the original integrand 1 over the square root of 1 minus x squared. So the key message to take away from this slide is if you see a pattern like this, think about the need for a sign substitution and realize that in this change of variables, the angle theta is going to be between minus pi over 2 and pi over 2, and that means the cosine of theta is positive. Okay, let's look at the differentiation on the next slide. So what we've seen up to now is that the integral of 1 over the square root of 1 minus x squared is arcsine of x plus some integration constant. And of course, every time you have an integral, you get a free derivative. So what this is telling us is that the derivative of arcsine is the integrand. In other words, the derivative of arcsine is 1 over the square root of 1 minus x squared. So let's check this by differentiating it. So let's say that y of x, a function of x, is arcsine of x. This means if we take the sine of both sides, we have the sine of y of x is equal to the sine of arcsine, and that is just x. And now we differentiate it, and we can call this implicit differentiation, or we can talk about just using the chain rule. But what we're going to get is the following. The derivative of sine is cosine. We don't change the argument, so we get cosine of y. I'm not going to write y of x explicitly, but we know it is. Multiplied by, we're using the chain rule, the derivative of the argument, so that is dy dx. And on this side, on the right-hand side, it's 1, the derivative of x with respect to x. So therefore, we have that dy dx is 1 over the cosine of y. Now, what do we know about y? Well, x is going to be between plus and minus 1 to keep the argument of the square root positive or 0. And the arcsine is going to be defined, because this is how arcsine is, to be between plus and minus pi over 2. For that range of angles, so for y between plus and minus pi over 2, we know that the cosine function is positive. So that means that we can write dy dx as 1 over the square root of cosine squared of y, and that's the modulus of the cosine, but we can write this because we know that cosine is positive. And that means that this is 1 over the square root of 1 minus sine squared of y. And now we know that the sine of y is equal to x, so this is 1 over the square root of 1 minus x squared. So we see indeed that the derivative of y, in other words, the derivative of arcsine of x, is equal to 1 over the square root of 1 minus x squared, as we had wanted to show. So having verified our integral here by differentiation, what I'm going to do on the next slide is give you a similar question and ask you to integrate it and to verify your answer by differentiation. And if you need it, I will also give you a hint, but you can try it without looking at the hint. So here is another exercise in the same vein for you. Show that the integral of 1 over 1 minus x squared to the 3 halves with respect to x is given by this. And then having calculated the integral and shown that this is correct, what I would like you to do is to verify it as well by differentiating this side and showing you obtain the integrand. Now, I will in a moment just talk you through the integral, but I suggest you try to do it before you listen to those comments. So I suggest you stop now and try it on with pen and paper. Okay, welcome back. Here's the hint. Okay, so you look at the integrand. The integrand contains a factor of the square root of 1 minus x squared all cubed. That's what this means. So you're going to make a sign substitution because there isn't an x in the numerator to make this something we could do by inspection. So the integrand is going to become 1 over the cosine cubed. And it's the modulus of the cosine, strictly speaking, but because of how arcsine is defined, the angle is going to be between plus and minus pi over 2, so cosine is positive. So what we have for the integrand is 1 over the cosine of our angle cubed. Now, because we're changing variables, making a sign substitution, there is going to be a dx d theta, or whatever you're calling your new variable factor, in here as well that we have to insert. And dx d theta gives you a cosine. The 1 over cosine cubed and the cosine here partly cancel, so you get 1 over cos squared, and that is sec squared. The integral of sec squared is tangent, and then from that, if you think about how tangent is defined, you should be able to obtain that. And then when you differentiate this, working backwards, you will get two terms, put them on a common denominator, and they will give you this. With that, I will stop the video.